Welcome back to sessions on energy equation as a part of introductory course on computational fluid dynamics. So we have already discussed about other two governing equations, which is continuity equation and momentum equation. So today we are going to continue with the energy equation derivation, which is one of the governing equations which we come across in CFD. So this is the outline of today's sessions. We are going to begin with assumptions, followed by the governing law on which we are going to develop these governing equations. Then the approach and flow model, what we are going to consider to develop this governing equation, which is energy equation. Then what is the physical principle we are going to apply so that we can end up with the final expression for the energy equation. Then followed by the derivation part, and at last we are going to conclude the session with reduced forms of equations. So as we already discussed, list of assumptions include flow is assumed to be continuous, then no viscous dissipation. So as we all know, viscous dissipation will impact the energy of the system, and electromagnetic forces are assumed to be negligible. Along with that, we are considering there are no chemical reactions. This ensures that even change in phase of the fluid can impact the energy of the system. So total energy must be equal, and it should not be converted into any of the other forms where there can be heat releasing and all, which makes the system of the equations very complex. So due to that, we are trying to consider the concept of no chemical reactions, so that heat of reaction or heat of change in phase will be considered to be negligible. Then we consider nuclear forces to be 0 or negligible, and phase of the fluid to be uniform. That is, if it is water, it has to be considered as water throughout the derivation, and if it is air, it has to be air. So it can't be air and water vapor in a single system. So it has to be a single phase system where due to change in phase, the energy may not be varied. Now let us move on to the governing law on which the energy equation is developed. The governing law is law of conservation of energy, which states that energy can neither be created nor destroyed, but can be converted from one form to other form. For example, heat energy can be converted into work, which we have been seeing in most of the engines, and work can be converted into heat, which we are seeing in refrigerators, so and vice versa. So energy can be converted from one form to other form, but it cannot be destroyed. That means cannot be brought to 0. So total change in energy of the system has to be 0. So coming to approach and model. So we are considering Eulerian approach, where we are going to consider control volume fixed in space. As you can see, it's control volume having total volume of V and total surface area of S, and if we are considering elemental volume, that will be dV, and elemental surface area is represented by ds, and you can see this is the velocity of the flow, the total velocity of the flow in along the direction, where ds indicates surface area normal to the flow direction. So with this is a control volume which we are going to consider for our derivation purpose, and it is assumed to be fixed in space. Next, the physical principle. The physical principle on which energy equation is derived is first law of thermodynamics, which relates different forms of energies in the thermodynamic system to that of the work done by it. So it states that the amount of heat added to the system will result in work, and some part of that heat is converted into changing the internal energy of the system or raising the internal energy of the system. For example, if we consider a container filled with water, which is fixed with a lid, or you can consider it as a airtight lid. So when water boils, this pressure will move this lid on top, producing some work done. At the same time, the heat energy will increase the internal energy of the liquid inside that container. So this is nothing but whatever heat energy is added is converted into raising the temperature of the fluid, and work is done by pushing this piston. So whatever heat is supplied will be converted into raising temperature, which is increasing the internal energy of the system. At the same time, the displacement of piston is the result of work done by the gases or vapor, which is produced due to heating of that particular liquid. So this is a simple analogy or the physical principle what we are going to use to develop this particular equation. So you can consider this as rate at which heat is added to the system should be equals to rate at which the internal energy changes and rate at which work is done by the gases. So to be simple, we can rewrite this in mathematical form as dq plus dw is equals to dE, because work is done by the gases, so it will have a negative sign. It has to be changed. So dq plus dw equals to dE. We can rewrite it in alternate forms based upon the direction of the work done, whether it is done by the system or onto the system. Based on that, the sign of this will change. Now let us consider certain aspects. Let Q be the heat added or rate at which heat added to the system per unit mass. That is, if Q is total heat added per unit time, that is capital Q dot, then this can be written as Q dot, which is rate of heat added per unit mass, into mass of the system. So what is mass for a system? Mass for a system can be written as rho into volume. That is, density into volume is nothing but the mass. So if we multiply this two, we'll end up with the total heat rate that is transferred to the system. Similarly, let us consider internal energy. Let internal energy per unit mass be E plus V square by 2. E plus V square by 2 is the total internal energy of the system. Then work done. So work done can be defined as a product of force and the displacement. So here we need to consider the forces which are acting in the system and the displacement what it cost. For example, in case of the piston, in case of this piston, the work done by the gases can be predicted by using P, that is pressure inside, into area of the piston which is exposed to the vapor or gases. In this is nothing but the force part, and the displacement whatever it is happening, delta x or delta y. So P into A into delta x is nothing but the work done by the gases onto that particular piston. So here we need to understand what are the forces we are going to consider for this particular derivation. So since we already assumed that the forces such as nuclear forces and electromagnetic forces are negligible, we can reduce the forces to be very few, that is pressure force, shear force and the body force. So these are the three forces what we are going to consider throughout our derivation. So these things we'll be discussing in further part where we are going to actually derive the equations. So before deriving, these are the considerations what we are making. So as I said, we are going to consider only pressure, shear pressure and shear stress, then we are going to consider body force. So pressure from this, pressure force you can say, shear force instead of stress, we can call it as shear force, and body force. These are the three forces what we are going to consider. So let us move further for mathematical model. So mathematical model is the basic relation which we are going to employ. So earlier we have seen that first law of thermodynamics, dq plus dw equals to du. So same thing we are going to apply for the particular scenario, that is, let B1 be rate at which heat added to the fluid inside the control volume from the surroundings, and B2 be rate of work done on the fluid inside the control volume, and last one, rate of change of internal energy of the fluid as it flows through the control volume. So from the first law of thermodynamics, we can rewrite these three as B1 plus B2 is equals to B3. So there is a slight correction. We can consider this as plus B3. It's okay. B1 plus B2 equals to B3. So where B1 is equals to rate of heat added, B2 is rate of work done on the fluid, and B3 is internal energy. So let us begin with the derivation part. So first, heat, as I mentioned, Q dot is the rate at which heat added to the system per unit mass. So if we consider the control volume, the elemental volume what we considered was dV. Elemental volume was dV. So if rho is the density, then for the elemental volume dV, the total heat transfer rate or the total heat exchange rate will be rho Q into dV. So if we integrate it to whole volume, the total heat added to the system will be equals to integration or volumetric integration of this particular term. So this can be written as V1 is equals to rho Q into dV, where V is the volume and Q is, as we already discussed, is rate at which heat added. Rate at which heat added to system with per second you can consider, and rho is the density of the fluid. Similarly, let us consider the change in internal energy. The second part, that is internal energy of the system. So internal energy changes will be contributed because of two aspects. First one is surface aspects. Second one is volumetric aspects. So since we have considered E plus V square by 2 is internal energy per unit mass, so change in internal energy through surface. Change in internal energy through surface can be written as rho into ds. This is multiplied with velocity will give me the rate of change of internal energy that is contributed through surface. So it's something like m dot into E plus V square by 2, where m dot is mass flow rate through that surface, ds. So m dot can be written as rho V into ds. So you can write the equation for contribution of surface through change in internal energy as rho V ds, which is the term for mass flow rate, and E plus V square by 2 is internal energy per unit mass. So similarly, the volumetric contribution can be written as dou by dou t of rho E plus V square by 2 into dV. Here this V corresponds to velocity of the fluid and this corresponds to volume. So these two are different types of V's which we come across in this derivation. One is velocity, other one is volume. So you can see volume has a curved right side part and this is a flat part. So surface contributions can be predicted with this, and volumetric contributions can be predicted or calculated using this relation. So dou by dou t of triple integral rho dV into E plus V square by 2. So these are the volumetric contributions to the change in internal energy. Then we have work done. So for the work done, we have considered three forces. First force being body force. First force being body force, second pressure force, and third shear force. So three forms of forces we are considering. So body force, if I consider F as the body force per unit mass, F is body force per unit mass by mass. So I need to multiply it with mass, and rate of change of work done can be written as F into velocity, force into velocity. So the contribution of body force to the work done is rho F V, where here V is velocity and here it is volume. Now similarly, contribution of surface forces. So we have seen two surface forces, one is pressure force, other one is shear force. So pressure force is nothing but P into A, area on which it is acting. So here area is ds, and multiply this with velocity to get work done contribution from pressure. So what is work done from pressure is minus P ds into V, where V is velocity. Similarly, shear tau ds into velocity. So this is the total work done. Now if we sum up the equations, so we have considered work done, we have considered heat, rate of change of heat energy, rate of change of internal energy, and at last we have now got what is the total rate at which work is done. So if we combine these three, we'll end up with one single equation, which is nothing but our energy equations. So you can see, so rate at which heat is added plus work done. This is work done due to pressure force. This is work done due to body force. I think one term is there, that is tau V ds with a surface integral, which is shear force contribution to the work done, is equals to dou by dou t of rho into E plus V square by 2 into dV plus rho E plus V square by 2 V into ds. So this is called energy equation in integral form. It's called energy equation in integral form. Now if we consider flow to be inviscid, then the shear forces can be neglected and your equation can be reduced to this. So basically this is the expression for energy equation for inviscid flows. Now if we consider body forces are absent, then your equation can be reduced to these terms. Now if we still consider that there are no body forces, no viscous forces, and flow is assumed to be steady, then even this term can be equated to 0. So you'll be ending up with q dot rho dV minus P V ds is equals to surface integral rho into E plus V square by 2 to V ds. This is the reduced form of energy equation for steady inviscid flow with no body forces. Now if we consider that heat added to the system is 0, that is if it is adiabatic flow condition, then you can still write this equation as surface integral PV ds is equals to rho E plus V square by 2 V ds, the surface integral. So if we further reduce this, we can further reduce this as the integrations can be cancelled and velocity can be cancelled. It can be written as P is equals to rho into E plus V square by 2, which can be written as minus P by rho is equals to E plus V square by 2 equals to constant, or E plus V square by 2. P by rho can be E plus P by rho. This term can be written as enthalpy, where I know that enthalpy can be written as S plus C. This is integration constant, so E plus P by rho can be written as H. So with this I can say that H plus V square by 2 equals to constant C. So this is an alternate form of energy equation which is purely in terms of enthalpy of the system and velocity of the fluid. So this is about your energy equation. So we started with assumptions, and then we discussed about the mathematical model, governing laws on which the energy equation is derived, followed by the derivation. And at the end, we consider various cases, or we reduce the energy equation to various cases, which includes for steady inviscid flow and steady inviscid flow with no body forces, and we can say final expression which can be called as for one-dimensional equations, which is H plus V square by 2 equals to constant. So this is today's session. Thank you all.